Hello, everyone, and welcome to this free webinar presented by WePassed. My name is Christina Ruiz, and I will be your moderator this evening. I will stop the presentation to review. There will be 5 multiple-choice poll questions, which you will be able to answer in the sidebar. Please go ahead and answer these questions as they come up. A minute to answer the questions before we go over the answer. During the webinar, please feel free to use the chat window to ask questions and discuss the topic. We'll take time after the presentation to answer these. This and other recorded webinars will be available to WePass subscribers. You can register through wepass.com to become a subscriber. Tonight's topic is What You Need to Know About Medical LINACS Part 1, presented by Timothy Waldron, MS, from the Medical Physics Group and Radiation Oncology Department at the University of Iowa Hospital and Clinics. Thank you for joining us, Tim.
Thank you very much, and good evening. So I'm Tim Waldron. I'm a medical physicist, about 100% clinical, and we're going to talk tonight about what hopefully you need to know about medical LINACS. I do have some conflicts of interest disclosures to declare, but nothing current. My employer likes me to tell everyone what companies I own stock in, and there they are. So tonight's learning objectives will be for us to all become familiar with really medical electron LINACS. I won't be covering other types of accelerators. And we're going to be focusing on acceleration and beam generation. So we're going to talk about acceleration via static forces, acceleration via electromagnetic waves, and of course that's going to require some resonant cavity understanding and accelerating structures. We'll talk a couple of times about beam energy control, microwave sources, high voltage supply for the microwave sources, electron sources, dose rate control, and finally bending magnets. Everything after the bending magnet we hope to cover in a subsequent Part 2 webinar. So let's get going. So if we want to accelerate electrons, we can do it quite easily by placing an electron in an electric field. An electron in an electric field is going to experience a force proportional to the electric field and the charge. So if I have an electron placed between 2 electrodes, this one has what I'm calling a positive potential on it, and this one has a positive potential, and this one has a negative potential. An electron in this electric field between these 2 plates is going to be accelerated to the right here, as shown by the arrow, and that's very straightforward. And so now what we have here is a static accelerator. We just need to find a way to create this electric field at the field strengths we want so that we can accelerate electrons to millions of electron volts. And therein is where the technicalities begin to overtake us. So let's get a little more realistic here and talk about an evacuated cylinder, shown here, an electron source, which I'm just going to leave sort of without detail, a couple of electrodes, and we'll just put 5 million volts between these 2 electrodes, and electrons will be accelerated from left to right. And when they exit, they're going to be at 5 MeV energy. And that's great, except for this whole 5 million volts problem. If we want to establish a static potential of 5 million volts, we need some rather large insulating structures. On the left here is an image from Bill Barletta, who runs US Particle Accelerator School, of the injector portion of the Bevatron at Fermilab. Here they were just accelerating ionized hydrogen to 750 keV, and you can see that this is quite a massive structure. And this was a Cockcroft-Walton high voltage generator, and you really need a lot of space to maintain these kinds of voltages in the static setting. On the right, of course, we've got the famous Van de Graaff generator. This one is 5 million volts, and so this one was accelerating things to 5 MeV. This very same one lives in the Boston Museum, and you can go see it do its job every day. If you have a chance to go there, I highly recommend it. So the problem here is that static accelerators are huge. So how can we get more energy in less space? we want to have clinically useful beams. That means in the MeV range. Clearly, there are limits to the static method. So maybe we can use an accelerating potential somehow. If I have an electric field or an electric wave that is sinusoidally varying and moving from left to right with a frequency and a time constant, if I put a charge in the vicinity of this varying electric field, it will be accelerated first one way and then the other as the field passes. However, if I could somehow shield that charge from the unwanted polarity of the passing potential, I might have an opportunity to get a charge to be accelerated by only the one polarity or the other, and therefore have some chance of being sequentially accelerated to the right. Of course, we'd only get accelerated once to the left here. And this is fundamentally what we would call a drift tube accelerator, first proposed by Leo Szilard in 1928, but also in 1928, one was built by a guy named Rolf Wiederow. His was an evacuated tube with a series of cylindrical electrodes placed in it. Alternating electrodes were fed with either polarity of an alternating current source, and ions, which were inserted at one end, had an opportunity to be accelerated in one direction or the other in the gaps in between each of these electrodes. So if we look at this structure and the arrangement of the electric fields, I have an electric field to the right in this region here, one to the left between this electrode and this electrode, one to the right in this gap, one to the left in this gap, one to the left and one to the left here, one to the right here. And this is simply the alternating current being applied at one instant in time. If I look at it 1/2 of a time constant later, of course the polarities are all reversed. The force field across each gap is now in the opposite direction. So if I set up my timing correctly, and I set up the lengths of my drift tubes correctly, and note here as we move from left to right, the drift tubes must be longer in order to shield the higher and higher velocity particle from the potential as it passes through them. In other words, it takes, the gaps are the same distance. The potential across the gaps are the same. So the amount of energy the particle gains across each gap is the same. However, because it's moving faster, it's going to travel much farther during the unwanted polarity of the accelerating potential before it reaches the next gap. If we want to build one of these things, and we want to get anywhere near relativistic, if I'm saying the relativistic beta is 0.1 for this arrangement, and the drift spaces are going to be around 10 centimeters, that means I'm going to need about a 1.5 gigahertz sine wave being fed in here. This is not going to propagate well on wires. As it turns out, Wiederow accelerated potassium ions to 50 keV with a 1 megahertz source back in 1928. The greatest difficulties he probably experienced at that time were with vacuum and the RF source rather than the design of the accelerator itself. E.O. Lawrence, who built the first cyclotrons, is credited with considered this to be his inspiration for the cyclotron when he saw this design. We're going to start talking about electromagnetic fields now, and I wouldn't be able to call myself a physicist if I didn't at least mention Maxwell's equations within this context. We're not going to spend a lot of time on this. However, there are a couple of important things about Maxwell's equations that are just evident, and I'm just going to state these things. First of all, from Gauss's law, we get the idea that electric field lines diverge to and from and terminate in charges, or in macroscopic structures, conductors. Magnetic field lines are continuous and do not terminate. In other words, they're not going to be able to enter conductors. And the total magnetic flux through a Gaussian surface is 0. Faraday's law, of course, a time-varying magnetic field induces an electric field, and Ampere's time-varying electric field induces a magnetic field. These two together tell us electromagnetic waves can propagate in space, probably the most important thing we can say about Maxwell's equations in this context. Now, if I want to try and propagate a wave using Maxwell's equations, I have to rewrite with no charge density, take the GURL of the non-zero equations, and I get a result that is in the wave equation, or equation of motion form, and of course it's second order. And if we just say, okay, we're going to get solutions to this, and they're going to be plane waves, they're going to have this form here, they're going to be cosines. And we're going to have some characteristic constraint with regard to the speed of light and the frequency going here. Once again, that same form above. And of course, this describes an electromagnetic wave propagating in free space that has electric and magnetic fields that are perpendicular to the direction of travel and to each other. They vary sinusoidally in time with a frequency of omega and a wavelength of lambda, which is equal to 2 pi over k naught. Of course, we said that k naught has this relationship here. And the two have the same phase. This should be somewhat familiar to everyone in this audience. So if we take a look at a representation of this, we get this here from Wikipedia. And of course, the red components are representing the electric field. The blue components are representing the magnetic field. We see we have lambda marked out for one wavelength. And of course, the wavelength is the distance between two equal phase points on one or the other of the two sinusoids. And this electromagnetic wave happens to be propagating down and to the right along what is the y-axis in this representation. By itself, this is of very little use to us in terms of accelerating electrons for medical use. However, I think we should understand it if we're going to use it to do that acceleration. What we can do is constrain our electromagnetic wave to a container. And we can cause it to propagate between two parallel conductive plates, and we can get there by solving that equation of motion such that the field at the edges of the plates are set to 0. We'll then find that we have a cutoff frequency of propagation that is related to the spacing and the dimensions of the two plates. And what we'll see is we get electric fields that are oriented in the direction of the red arrows shown, and magnetic fields that are circulating around in the orientation of the blue arrows. Again, this is not especially useful if I want to accelerate electrons along this direction of propagation. If I were to place some electrons in the influence of these magnetic fields, they would simply bounce up and down without going anywhere, and they would have no net acceleration. But if I look at my drift tube LINAC and I say, hey, the acceleration occurs here in these gaps between the drift tubes, maybe I could borrow this geometry and somehow apply my electromagnetic wave just to it and maybe get some acceleration out of that. So let's go ahead and take that geometry, which is just a cylindrical container, and let's set some boundary conditions. Let's say that the electric field is going to be 0 at the walls, which are r equals big R, radius is r. And we're going to set it to be 0 at the ends. We're also going to say that the magnetic field is going to be 0 at the walls and parallel to the walls. Of course, that's going to happen anyway, thanks to Maxwell's equations. If I want to propagate a wave in this cylindrical geometry, my solution is going to have a Bessel function in it. And I'm going to jump ahead here and remind everyone that Bessel functions are simply functions that allow us to deal with waves in cylindrical coordinate systems. And we're mostly interested in the zeros of the Bessel function. In other words, we're interested in the 0th Bessel function, and we want the 0, 1 version of it, and that corresponds to 2.405, which is this 0 here. We could also use any of the zeros of this one to get propagation within the cavity we're talking about. These other versions of the Bessel function would give us different modes of propagation. So I have this function that tells me something about the electric and the magnetic fields propagating within this can. And what we're going to get is that the resonant frequency, or really the cutoff frequency, is going to be the resonant frequency, excuse me, the first resonance is going to correspond to that 2.405 number, which is that first 0 of that first Bessel function, that 0th Bessel function. And we can see that we have a resonant frequency. We have this 2.405, and that's going to tell us the radius of this cavity in order to get propagation or resonance. And when we do get that, what we're going to get is electric fields oriented left and right, surrounded by alternating magnetic fields, which are circular in their behavior. Now, this will be very handy if we wish to accelerate electrons along the axis of this structure, and of course, that's what we're getting at. I now have an electric field in a direction that is useful to me in terms of accelerating electrons. So let's go ahead and skip back through Bessel functions. So now I have a resonator. I have a cylindrical conductor that if I can get an electromagnetic wave in there, it will resonate there and it will give me the fields and the orientation that I need. And so then I can maybe use it to accelerate electrons. Well, as it turns out, our boundary conditions are very helpful to us because the ends of this container are at 0. Therefore, if I want to just cut a hole in it, I can. So we'll cut a hole in it. And now, when the electric field is oriented to the right, if I place some electrons near the opening, they'll be accelerated to the right or to the left, depending upon where they're at when that polarity switches. In terms of designing a physical length through our structure, we're interested in a particular transit time, right? The time that the particle takes to cross our cavity has to be useful to us in terms of the energies that we wish to reach on acceleration. And so the time constant over 4 has to correspond approximately to the time it would take for a light wave to propagate through there. So that's going to constrain us to both our resonant frequency and our physical size. Luckily, these can be realized in reasonable size, even with this constraint. So let's take a bunch of these and stack them up. So if we stack a series of pillbox resonators together with these holes in them, we can now propagate an electromagnetic wave through here. So here's a snapshot in time of the fields for a wave that is propagating through. I'm showing a large electric field to the left in this cavity, a not quite 0 electric field to the left in this cavity, perhaps approaching 0 and switching over, followed by 1 to the right in this cavity, 1 that's close to 0 in this cavity. And of course, as these propagate through, each cavity will see all phases. So a little time later, this one will have 0, and this one will be to the left, and this one will have 0, and this one will be to the right. And I have an animation that doesn't quite work the way I always like here, but you can see the fields are pointing left and right and sort of propagating from left to right. Do that one more time. That one, that one, that one. So if an electron is inserted at the right time in this cavity, it will be accelerated to the right, drift, accelerated to the right, drift, and so on and so forth. Well, now we've got a linear accelerator. In fact, we have what we call a traveling wave, a linear accelerating structure. So now I'd like to talk a little more about the structure of the rest of this lecture. We've introduced the concept of an accelerating structure. We're going to be talking about sources of particles for injection, sources of RF, or our accelerating potential, the high voltage needed to operate that RF, and the bending magnet system, which ultimately will select energy for us. The target, flattening, dosimetry, collimation, etc., and details of everything after the bending magnet will be covered in the next lecture. So accelerating structure, I'm now going to talk about accelerating structures in the more applied context. So we're done with the theory. So traveling wave accelerating structure. Packets of RF energy, the electromagnetic waves I was talking about, are injected at the proximal end, propagate through the accelerator, and are extracted at the distal end. Instantaneously, half of the structure, the fields, are approximately zero. And of course, that one it's leaving, so I left it empty. Of the remaining half, half of those are accelerating to the right, and the other half would be accelerating to the left, or I should say the field is to the right and the field is to the left. Due to resistive losses, the field amplitude will decrease along the length of the accelerator. So we are ultimately limited in how long we can make one of these things for a given amount of RF input. Cavities are slightly longer at the proximal end and tend to be of equivalent spacing at the distal end. At the proximal end, the transit times are changing because the particles are increasing in velocity. Once they become relativistic, their velocity remains constant, so the cavities are the same size. And in a traveling wave LINAC, we're looking at something approaching 2 meters length to get to 20 MeV. And by the way, I'm using a disk and washer representation for the traveling wave accelerator. Although if we were to cut a modern traveling wave accelerator in half, such as on one of our Electa machines, we would see the cavities don't look like this internally. This would work just the way it's shown. However, it's not an accurate representation of a modern machine. So the next type of accelerator that we would encounter is a standing wave accelerator. And a standing wave accelerator takes advantage of the fact that if I have two waves that are traveling towards each other in opposite directions, I have an opportunity to become a standing wave pattern. That is to say that the two waves can algebraically add and subtract to form what appears to be a stationary pattern of peaks and valleys. Even though both waves are still traveling to the left and to the right, they merely combine to give us this pattern in which I have peaks that are just switching between positive and negative, and 0 points that are modes and nodes that do not seem to be moving at all. And the standing wave is generally the twice or nearly twice the amplitude of the two waves coming from the opposite directions. If we were to cut a modern traveling wave accelerator in half, the cavities might look more like the way these do here in this drawing. So if we were to take that and simply replace one of the cavities with a half cavity on the end, what would happen now is when we put RF energy in here, or electromagnetic waves in here, they will not simply process from one end of the accelerator to the other. They will tend to reflect around the inside. And just like the two traveling waves opposing each other in the preceding slide, if we wait a little while after we begin pumping electromagnetic waves in, we will observe a standing wave pattern. The time it takes for this to happen is called fill time. There's a fill time and an empty time associated with putting the RF, switching on the electromagnetic waves into the accelerator and then switching it off again. It's a couple of nanoseconds, but it's there. So now what we have is we have this standing wave pattern. Now I have alternating cavities that either have 0 field or a field that is rapidly switching between maximum and minimum. or I should say switching between maximum and minimum with the time constant associated with the frequency of the electromagnetic waves. So I have now the same length accelerator, but now I have these zero field cavities that are stationary, and all these cavities are doing is propagating the RF. So maybe I can do something else to shorten my accelerator and make my equipment a little smaller. Maybe I can remove those cavities somehow. And in the standing wave accelerator, it doesn't matter where we feed the RF in. It's quite popular to have the input feed be at the halfway point or at 1/3 of the length of the accelerator. So let's go back to our cavity, our idealized can-shaped cavity. In the traveling wave accelerator, the electromagnetic waves are coupled through the central iris. But if I remember that, I can cut a hole anywhere in the wall of this, which is always at 0, and let the, what happens is when I cut a hole here, now I'm going to have little currents flowing around here because I have all this magnetic activity just behind it. So I'm going to have an induced current in the wall. This will, and it's alternating. So of course, if we go back to Faraday's and Ampere's laws, it's like, hey, I've got an alternating current here. That means I've got a magnetic field and an electric field that's going to be induced here. This now becomes the means for me to couple the energy in this cavity out of this cavity without using the central iris. So now what I can do is I can take my 0 cavities and move them off to the side and make my LINACS shorter by half. So here's the 0 cavities now coupled through that little iris opening in the side, in the out from the center. Here's the central iris. So now when the RF propagates, it propagates, say, in here, through this cavity, through this cavity, this cavity, this cavity, this cavity, and so on and so forth. We could say it sort of zigzags through there, although it's conceptual. So now my accelerator is half the length it was by using inductive irises in the side of the cavities. So now when an electron is inserted at one end, it enters a cavity and it is either going to be accelerated back out or to the right. It does not have a drift space. And when it reaches the next cavity, it will be accelerated to the right again and again and again. So we have serial acceleration in every cavity that the electron passes through. One point about standing wave accelerators, and that is that the RF is never extracted. It's largely converted to heat, and this creates some issues down the road. But on the other hand, our accelerators now between 100 and 120 centimeters in length to get a 20 to 22 MeV electron beam. But this is not a free lunch. As I said, they're highly reflective in nature, and a lot of the power is dissipated as heat, much more so than a traveling wave accelerator. And so we have much more stringent requirements, demands placed upon the RF system, and it makes the RF system more complicated. Here's a photo of a side-coupled standing wave accelerator cut in half. We can see that we would call this a half cavity here. We would call this a half cavity. All this is where it was cut. It's just a section of one. Here are side cavities, and here are 2 accelerating cavities. So the beam would pass left to right through these openings here. So if I want to get more energy, I can make my accelerator longer. The amount of acceleration depends very strongly upon the amount of RF power in each cavity. So if I have more cavities with the same amount of RF power, I'll end up with a higher energy. Or, more practically, if I have a fixed number of cavities, I can obtain a lower energy coming out of the accelerator, and I'm referring to what we call intrinsic energy here. Intrinsic energy refers to the electron energy, or really the electron energy spectrum, as it's exiting the accelerator and entering the bending magnet. This is not to be confused with the clinical beam energy or any of the other more precise descriptions of energy that we might find, say, in ICRU 35. We'll be talking about those details in the next lecture. So if I have an accelerator as shown above, and I'm putting power level 1 into it, and of course here's sort of a fake standing wave pattern, I'm going to get intrinsic energy 1 out. If I lower the RF power to this value I'm calling power 2, I'm going to get intrinsic energy 2, which is going to be less than intrinsic energy 1, because power 2 is less than power 1. It's as simple as that. Now there is one little detail, and that has to do with the fact that power 1 has a certain amount of work it can do on the electrons. Power 2 does less work than power 1. And it does take work to accelerate the electrons. So if I have a high energy or a high power level, the maximum electron fluence that I can inject into my accelerator and successfully accelerate to that high energy is not unlimited. This is going to affect dose rate ultimately. If I inject too many electrons per pulse, or too much electron fluence, what will happen is that it will slightly decrease my intrinsic energy. What will happen is the average energy will decrease somewhat. This is undesirable, and this is also why accelerators that use this method to control power generally have a higher dose rate at the higher photon energies and a lower dose rate at the lower photon energies. They just run out of work at the lower power level. One way that we can overcome this limitation is by effectively shortening our accelerator. Now here I have that same accelerator with this funny little red thing in the side cavity. And if I put power into it as I did before with the red thing extracted from the side cavity, I'm going to get my standing wave pattern as I showed before, and I'm going to get energy 1 coming out. If I insert this plunger, this is the energy switch by the way, into this side cavity at the correct point along my accelerator, I'm showing it at halfway here. So, so if this power level corresponded to say 10 MV as my energy, my beam energy, when I insert this slug into the side cavity, it effectively shorts out the side cavity, and the RF energy will simply not propagate past that point. Some will, but generally speaking, it turns this part of the accelerator into a drift tube. So now that means that I can accelerate electrons at this same power level through the first half of the accelerator, and I can load that beam just as much as I did for the higher power level. But now, because I'm not, the electrons are not undergoing acceleration in these other cavities, so the total energy is now much less than the energy in the case of E1. So the energy switch effectively shortens the length of the accelerator, allowing us to operate the remaining accelerating cavities at full power. The reason for doing this is to be able to have the same electron fluence available for both the high energy and the low energy. So here's our first question.
All right, everyone. So we are going to go ahead and get started. We're just going to take a second to get the poll question loaded up. And once that is ready, it'll be posted on the left-hand side of your screen. And we'll give you about a minute to respond, and then we'll review the answer.
I'd like to add that you want the most correct answer.
All right, Tim, I think we can go ahead and review the answers.
Okay. All right, so why might a manufacturer construct a LINAC using 2 accelerator structures in series? Answer A is for twice the acceleration at the same RF power level. That is not the most correct answer. That would be true at very low fluence levels, but why would you want to do that? E, to make the dose rate more stable as the gantry rotates. Well, that's downright silly. C, complexity equals profit. Well, maybe, but the correct answer is D. And very much like the case of the energy switch in the variant accelerator, the single accelerating potential cannot do infinite work. But if I take 2 accelerators and put them in series and feed each one a different level of RF power, I could obtain a high dose rate both in high and low energy photons by controlling the amount of acceleration occurring in each of the accelerators. And in fact, back when CGR was making LINACs, this was exactly how they got high and low photon energies at high dose rates, was by having one accelerate and then the other one decelerate. So moving along, one other type of LINAC used in medicine is the single photon LINAC, and of course these don't have a bending magnet. In a setup like this, we're going to have high voltage, RF, particle injection, an accelerating structure, target, and so on and so forth. In this case, beam energy spectrum now depends almost completely upon RF power and this beam loading that we talked about. This is less of a problem if I only have one energy, because then I can optimize these 2 parameters. But there are systems out there for which this is a non-issue, and which beam loading is deliberately adjusted in order to obtain particular beam characteristics. So we've talked about some of the dimensions of some of these things, and I've avoided being very specific because we really have quite a range of values in use. So here's a little table of power, size, and frequency for some common and maybe not so common medical electron accelerators. On the leftmost column, we've got the band. Frequency ranges from the military have letter designations for different bands. And so we have an S as in Sierra. S band is the most common medical LINAC band. Usually we're talking about a center frequency in the 2.8 gigahertz range, although we've got machines that operate from about 2.5 up to 3. For this range, the cavity radius is typically 4 centimeters. The cavity length is typically 5 centimeters. And if I want to get 6 MeV with a standing wave accelerator, the accelerator is going to be about 33 centimeters in length, or for this configuration, it's going to be 6.5 cavities. One interesting case is the accelerator in the Vero product, and that is a C-band accelerator, which was designed, optimized for medical use. These other frequencies we're utilizing off-the-shelf microwave stuff from military radars, really. Both S-band and X-band are heavily used in the military. So C-band, you can see we're higher in frequency, things are physically smaller, and we get a little more acceleration in a shorter space. Or I should say we get the same acceleration in a slightly shorter space. If we're looking at X-band, we're close to 10 gigahertz now. The cavities are much smaller. And this 58 cm 6 MeV number, I think this refers to the 2 accelerators in series that are used in Mobitron. I suspect you can get 6 MeV with an X band at half that. So I'm a little unsure about this figure. As frequencies increase, so does the theoretical maximum electric field in vacuum. So really, if I want higher energy, it's desirable to go higher in frequency because my breakdown voltage goes up for a given energy. But that doesn't have that doesn't come as a freebie either. As frequencies increase, sizes are reduced. Now I have a manufacturing problem. I also now have to have a much tighter frequency spec that I'm going to operate over. I don't know if this is going to work or not, but there's a very interesting simulation that's available at this webpage from CST. And I'm going to try and switch to it now, and we'll see what happens. So hopefully what you're all seeing now is an animation of a standing wave accelerator showing the electric fields switching back and forth. And if not, well, then I encourage you to go to the CST webpage sometime and look at it. I think this is a really nice illustration of the way the fields behave in a standing wave LINAC. This one happens to be what we call slot coupled. The zero field cavities are not fully off to the side. They're performing that same function of propagating, and we can see that we have 1, 2, 3, 4 cavities that are accelerating cavities. We can scroll down here a little lower, and we can see that there's actually a particle simulation going on here for about a 6 MeV electron beam. And it's nice to see the particles just spilling around in there under the influence of the electric fields. I'm going to go back to the slides now and continue on. So thus far, we've talked pretty much strictly about accelerating structures within our generic medical LINAC. Back to this block diagram again. So I'm going to go on to RF system, which is my generic label for our source of accelerating potential. I've talked about electromagnetic waves going into accelerating structures, and so now we need to talk about where those are coming from. There are 2 types of commonly used sources of electromagnetic waves, or RF, or microwaves, in medical LINACs. The first one is the klystron amplifier. Now, a klystron amplifier is an amplifier. It needs an input. And the way a klystron works is I've got an evacuated cylinder shown here. The white parts here are vacuum. The orangish parts are copper. I've got 2 cavity structures, one at one end and one at the other end. On the left-hand side here, I've got a cathode. Now, by definition, anything I call a cathode gives up electrons, and it's heated by a filament. And so if I just heat that filament, a cloud of electrons will appear somewhere nearby. And nothing else will happen until I apply some voltage. And I'm going to apply some voltage between the very top, the anode of this structure, and this cathode. I'm going to apply about 120 kV. And I'm going to leave it on for about 6 microseconds. During that 6 microseconds, electrons are going to flow from left to right under the influence of this 120 kilovolts. Nothing much else is going to happen except we'll be making a lot of hot water up here. This thing has to be water cooled. Until such time as we begin to interact with these cavity structures on the side. Now this cavity here at the proximal end of the structure is called the buncher. And what we're going to do is we're going to couple in 3 gigahertz at a couple of 100 watts peak. Not a very high power level. And this is coming from something that is commonly referred to as an RF driver. Recall I said this was an amplifier. It needs an input. This is the input. And we're just going to send that in through an antenna. Just a little loop of wire somewhere in this cavity. Now this is a resonant cavity, so it's going to have a resonant frequency somewhere near 3 gigahertz. So as that energy is entering this cavity, it's going to set up a series of electric and magnetic alternating fields inside this cavity. This in turn is going to excite charges in the walls of this cavity, at a very thin depth, to begin to take on some of these characteristics. And what's going to happen is we're going to have an alternating electric field appear across this gap, and it will do so in a circularly symmetric way. This alternating electric field across this gap is going to modulate the velocity of this electron beam. We're going to have velocity modulation. When the electric field is to the right, electrons nearby will be accelerated slightly to the right. They'll get a little kick. When the electric field is to the left, some of the electrons nearby will be decelerated. And once they get past this gap, they'll just go on about their merry way off to the right. But of course, as that happens, we have some that are accelerated and some that are decelerated and some that are unaffected. So what will happen is the more highly accelerated electrons will begin to catch up with the decelerated electrons, and the decelerated electrons will fall behind the unaffected electrons. And this produces a bunching effect. So instead of a continuous stream of electrons, now I have a stream of electrons whose density is varying as a function of this 3 gigahertz entering the bunching cavity. This contraction of the bunching will increase as we get farther and farther from this point, until it hits a critical point where things are maximally bunched, and then they will begin spreading out again. And at this same distance again, it'll be a uniform beam, but of course we're not going to let it go that far. Here at this critical distance, this critical drift space, drift length really, we're going to place another resonant cavity. And it's going to be a cavity that resonates at close to 3.0 gigahertz. And now what I've got is I've got a gap here with a very large charge passing it. So as that charge passes this gap, it's going to interact with electrons near the surface of this conductor, forcing them counterclockwise and clockwise within this cavity. They're going to rotate back and forth, just a few charges. And they're going to do so sinusoidally as a result of the sinusoidally varying charge density passing this gap. This is going to induce a rather large electromagnetic field in this resonant cavity. And this is due to the increase of the charge density. The current here might be 80 amps continuous. The current here is 80 amps varying over a few nanoseconds. And that, of course, is that very high instantaneous current value produces a very large electromagnetic field in this catcher cavity. And we can now simply couple that electromagnetic field out of this vacuum through a window into a waveguide. Klystron amplifiers can easily have amplification factors of 1 times 10 to the 6th or 1,000,000. And it's not unusual to see 6 megawatts or 7 megawatts or 8 megawatts peak output on one of these things. So we are velocity modulating electrons in a buncher cavity and then extracting the charge density variation of that bunched electron beam in a catcher cavity. And then that is simply, we're exciting this cavity, or exciting charges within the walls of this cavity to set up a very, very high power electromagnetic field coming out of it. That's the klystron. It's an amplifier. The other device of interest here is the magnetron. Now, one way to think of a magnetron is to imagine that we can take our klystron and bend it in a circle. So now we can just have a circulating electron beam passing these cavity structures. And in fact, that's not a bad description of the way a magnetron works. Now, a magnetron is a crossed field tube. We've got an anode structure on the outside here. And in the wall of the anode structure, we have cavities. And these are RF cavities, and they are going to be somewhere, they're going to be sized such that their resonant frequency is somewhere of interest to us. At the center of this affair, we've got a cathode, a filament heated cathode that's going to give off electrons. And when we apply some negative high voltage to this cathode, those electrons are going to be driven off radially. Okay. But what we need to know is that we have a magnetic field along the axis of this structure, and it's oriented into the page. And this causes the electrons to spiral within the structure. In other words, electrons boiling off of this cathode here are going to circulate counterclockwise. Electrons are going to tend to circulate counterclockwise. Of course, if the magnetic field were the other way, they would simply circulate clockwise. And they're going to pass the gaps of these resonant cavities, which are here. And of course, the electrons are going to interact with charges in the walls of the cavity, not unlike the catcher cavity in the klystron. They're going to set up electromagnetic fields inside these cavities close to or at the natural resonant frequency of these cavities due to their particular size. One interesting point about magnetrons is alternating faces of this structure are physically wired together. In other words, there's a wire going from this point here to this point here, and from this point here to this point here. What this does is it causes the varying electric fields across the gaps of the cavities to synchronize, and it also reinforces the oscillation within the cavities and ultimately will sum these values to be output. One interesting feature of this is that by changing the size of one cavity, we can effectively change the resonant frequency of the entire structure. And so if we wish to operate this device at a different frequency, we just need to run a plunger into one of these cavities and the frequency will change. We're changing the resonant frequency of this cavity by changing its size. Therefore, we're changing the operating frequency of this device. So a magnetron is an oscillator. It is a natural full feedback. It is an amplifier with its input attached to its output. Notice I haven't said anything about inputs here. The electron beam is passing these cavities, and the energy is being exchanged between the electron beam, the cavity, and then the cavity back to the electron beam. And it's a process similar to the bunching and catching process that we talked about in the klystron, except it's happening over and over and repeatedly inside the magnetron. And with like the klystron, we're only turning this thing on for 5-6 microseconds at a time. So all of this is happening pretty quickly. Alternating cavities are wired together, and ultimately they are all wired to a dipole that radiates out into a transmission waveguide. Here's a photo of a magnetron with one side pried off. You can see it's a copper structure. The central silver thing in the middle is the cathode. It's a cylinder, so it goes full depth. And of course, electrons would be emitted in this direction. These little things are the cavities in the wall that I referred to. Here's one of those wires going out to the dipole antenna, and we can see that alternating cavity faces are wired together. So that wire goes out to here to one side of the dipole antenna, and then the other one, they all go to the other side. There's two sides to this. So the other side, the opposite side of this structure also has wires going out. Here's a view of the other side of this device. The electrical connections are here. Of course, the anode is ground. Here's the tuner motor attaches here that drives the plunger in and out of one of those cavities. This is generally surrounded by the pole pieces of an electromagnet to get our magnetic field along the axis. And here's a close-up of the dipole antenna at the bottom of this device. Now these two posts are going to the alternating cavity faces. And so we're summing all of the electric fields on those cavities so that this antenna can radiate them out through this glass dome into a circular transmission waveguide. If I want to make a comparison between klystrons and magnetrons, magnetrons in this column, klystrons in this column, a magnetron is an oscillator. It requires no input. A klystron is an amplifier. It needs an input. In general, klystrons are usually used in higher power applications than magnetrons, although I think the magnetrons currently used in the Electa machines are closer to this 7 megawatt number than this 3 megawatt number. So these are not hard and fast. These are just for comparison. Magnetron lives tend to be shorter. If I have a machine with a klystron in it, hopefully, I could go the life of the machine and not change the klystron, maybe. If I have a magnetron machine, I'm going to be replacing that magnetron every few years. But it's a much lower cost device. Klystron's high. A magnetron, I can use a permanent magnet for the magnetic field. The klystron doesn't inherently use a magnetic field. It does have a solenoid around it to focus the electron beam, although they can function without that. Small klystrons can. Magnetrons can be placed in aircraft at very high power levels, and so they're quite mobile. A high-powered amplifier, klystron type, is going to be difficult to put to operate in different orientations. It can be done, but it's quite expensive to do so. Here we are at question number 2. Uh-oh.
Hi, everyone. Sorry, it looks like Christina's microphone might not be working. So you can see the poll is available on the left-hand side of the screen. We'll give you about 30 more seconds to answer. All right, Tim, how about you go ahead and go over the question, the answers.
Righto. So a klystron amplifies microwaves by which of the following? Are we catching electrons in a cavity that bunches microwaves? No. Referring to the poll, most everyone got it right, by the way. Low power microwave input causes electrons to circle inside cavities. No, that one's silly. Force drift of an electron beam to bunched microwaves in cavities, also nonsense. Velocity modulation of an electron beam with energy extraction after a drift period. Yes, we velocity modulate the electron beam in a buncher cavity, and then that modulated beam excites the catcher cavity, which then develops, which then is excited and develops an electromagnetic wave that we can then couple out. I do need to refer to frequency control here very quickly. The resonant cavities that make up the accelerating structures are very high Q cavities. Now, what that means is that if we look at the amount of energy they accept as a function of frequency, where the central axis here is the resonant frequency, and we're looking at the frequency of energy going, the frequency of the electromagnetic wave entering the cavity is a function of frequency. We can see that a very high Q cavity accepts a very high amount of energy over a very narrow frequency range, and a lower Q cavity accepts a lower power level at its peak, but does not fall off as rapidly. In other words, this is a very narrow bandwidth device, and this is a very wide bandwidth device by comparison. Now, what this means is that when we have heating in our cavities, their physical size changes, which means they now are operating at a different resonant frequency. And so my accelerator absolutely has to have some means of maintaining resonant frequency over a range of energy. And this is especially true for the standing wave accelerators. So I have to have an automatic frequency control system. And you've probably seen reference to AFC. So acceleration occurs at resonance. We said that. We've also said that a significant portion of the energy being used for acceleration is converted to heat. So in a standing wave accelerator, the accelerator itself tends to reflect lots of energy if it's not at resonance. Therefore, we can have the AFC system simply monitor the amount of reflected power from the accelerator and then tune frequency until that is minimized. And that is, in fact, how AFC works on a standing wave system. On a traveling wave accelerator, these do not reflect a lot of RF power back out. They're a very well-matched load. They don't have a lot of the issues that a standing wave system has in terms of managing the RF. And what we can do here is monitor the phase shift of the electromagnetic wave at different points along the accelerator and then use that information in order to tune to the correct frequency for the selected energy. I do need to talk a little bit about how we get the RF energy from our klystron to, or our magnetron into our accelerator. So I'd like to refer back to our pair of parallel plates with our electromagnetic wave propagating between them. It's easy enough to turn this into a rectangular pipe by just sticking some walls on the sides because our boundary conditions say that everything is zero along these two surfaces. So we can just connect them together and say it's good. And that's just great because now I have a pipe that I can use to connect my magnetron to my accelerator. And now I have a means of getting the electromagnetic energy from that device into the accelerator to do the acceleration. And the cutoff frequency, the minimum frequency, which will propagate in the transverse electric mode. Transverse electric mode means that no component of the electric field is along the direction of propagation. Transverse electric, no component along propagation. Notice that compared to my previous slide, the long side of the rectangular tube is now A, before it was B. And basically, the frequency of propagation depends upon the width of A. So if we look at a transmission waveguide for a 3 gigahertz TE0 mode, the A dimension is about 7.2 centimeters, the B dimension is about 3.4 centimeters. According to our formula, this gives a cutoff frequency of about 2.08 gigahertz. That's the minimum frequency, so as long as we're above that, we should be fine. And most of our equipment operates between 2.5 and 3 gigahertz. Furthermore, this formula gives the cutoff frequency for a dry air-filled waveguide. If our waveguides were filled with air, they would arc over very rapidly. Air simply just doesn't have enough of a dielectric strength to withstand the strength of the electric fields we're putting through there. Most medical LINACS have waveguides pressurized with sulfur hexafluoride gas, typically at about 2 atmospheres. So from a maintenance perspective, we now have this other problem in that we have this really hazardous gas in there that we have to keep tabs on. Should the pressure drop low enough, of course, we'll lose that dielectric constant and things will get nasty pretty quick. Another device I need to speak about is a waveguide circulator. If we talk about the standing wave accelerator as highly reflective, a large fraction of the power we send to that thing is reflected backwards towards the source. Now, that's not a very good thing because that means we're going to have standing waves occurring in our transmission waveguide, which is already close to maximum electric field capacity. And we don't want that happening. So we have a device we call a circulator. Now, this is simply a junction of several RF waveguides with a central ferrite placed in the middle of it. Now, It's really a ferrite with a magnet. So we've got a magnetic field into or out of the page. And ferrite and the magnetic field together give us a thing called Faraday rotation. And it simply acts as a rotational transform for the electromagnetic wave coming from the RF source. It makes it turn right. And it makes the reflected power turn right. So we can simply add a section of waveguide with an absorptive material in it. This is what a dummy load is. It's a section of waveguide walled off with water flowing through it or with some resistive material in it that simply converts the energy into heat. So now, of course, the reflected energy is not going to harm our RF source and the power gets to the accelerator. Some systems used 4-port circulators. Older Varian machines use the 4th port to actually control the power level going to the accelerator. And so there are both 3-port and 4-port systems out there. Here's a photo of a 3-port circulator. Here is the dummy load, or the energy absorbing load. Here is the input. Here is the output. The ferrite and magnet are here underneath this circular thing. And so if we have RF power going into the input, it is going to be cycled around to the output through Faraday rotation. And of course, any RF power coming in the other way is going to be cycled to the dummy load. So we've talked about accelerating structure and RF system. Now we can talk about our particle injection, or our source of electrons. We need electrons. Anything that emits electrons is nominally known as a cathode. There are I'm going to use 4 words to characterize cathodes. There are really just 2 types of cathodes. There are oxide cathodes and dispenser cathodes. They generally run at slightly different temperatures, and they have different emittances in terms of the current per surface area. You can see oxide cathodes 1 amp per centimeter squared, dispenser cathodes 100 amps per centimeter squared. Usually we're talking about structures made of tungsten, barium, calcium, aluminum, and frequently these are coated with iridium, ruthenium, or osmium. This coating helps keep the surface from cracking. You know, they're cycling through very high and low temperatures as we turn the machines on and off, and this keeps these from cracking and flaking. Oxide cathodes, strictly speaking, are usually barium or thorium oxide. Newer ones are made of these exotic cerium hexaboride and lanthanum hexaboride. They operate at much higher temperatures, longer life, higher materials prices. For our medical LINACS, we're here in the tungsten and oxide and dispenser range of cathodes. There are both direct and indirect heating cathodes. Now, a directly heated cathode for us is almost always going to be an oxide cathode. So it's going to be a tungsten wire, and it's going to have enough current flowing through it to undergo thermionic emission. Thermionic emission is the result of electrons being released from the lattice of a conductor due to their energy level simply being raised high enough to escape the lattice. And we can obtain that by heating, and the most efficient way of doing that is by running current through it. Again, these are typically 800 to 1,000 degrees centigrade, 1 amp per centimeter squared. As these age, the surface area increases. And so as these age, the gun current increases under otherwise fixed conditions. So for my directly heated machine, if I watch gun current, I might be able to predict failure. An indirectly heated cathode is a dispenser type. And here I actually have 2 separate structures. The cathode structure itself is one part, and then inside of it is a hot filament which heats it. And these run closer to 1,100 degrees centigrade, and of course have a higher emission per surface current, per surface area. And of course, there's a little graphic of that. So we have 2 types of electron guns. If we remember, we have the diode and the triode electron gun. In both cases, the anode is the accelerator. The cathode is the emitter. So a diode has 2 elements. A triode has 3 elements. In both cases, only one element is emitting anything. A diode has 2 elements, but it one element is emitting, and it's the cathode. So here is a diagram of a directly heated oxide cathode diode gun. The cathode is a filament, so it's a filament of wire, usually tungsten. It's being heated by running current through it. I have a focusing electrode here, which is this sort of parabolic shaped thing. And I have the high voltage being applied to the cathode. When the filament is heated, electrons are going to boil off. When I apply high voltage to this cathode, and this is a negative high voltage, remembering that the accelerating structure is the anode, electrons are going to be accelerated from left to right. If I also apply maybe that same high voltage to this reflective structure, it will tend to focus them into the opening in my accelerator. If I want to turn the electron beam off, I can turn off the high voltage, but I also want to cool the filament a little bit because it's going to continue emitting. Okay, so we're not going to turn the electron beam off and on very quickly on a diode gun. Here's a photo of a diode gun. This is one out of an Electa machine. This is the reflective structure, and so this gets a high voltage placed upon it when we want to shoot some electrons into the accelerator. Here's a close-up of the directly heated oxide cathode. It's a coated tungsten wire that we're running current through, and it is the cathode, and it emits the electrons. Here's the view of the backside of this system. One of the interesting things about the Electa injector or gun is that the back covering of it is glass, and if you happen to walk back there, you'll see this thing glowing. So the backside of that structure we were just looking at is here, and we can see that there's something glowing just beyond it. Here are the two wires going to the filament, and they will also be, the high voltage will be applied the same to both of them in order to force the electrons off of there when we want to send the pulse through. The other type of gun that we find in medical accelerators is the triode electron gun, triode referring to 3 elements. And so here we have the anode, which is the accelerator. We have the cathode, which is emitting the electrons, and we have a grid. We have a filament that is heating the cathode. In most of these cases, it's an indirect, it's a dispenser type cathode, so it has a separate heater and cathode structure. The filament heats the cathode, electrons are boiled off, and as long as the voltage on the grid is negative with respect to the cathode, the electrons will not pass through the grid. The grid is very close to the cathode, and so inverse square force says that the electrons are just, they're going to see that grid and they're not going to see anything beyond it. This also has a focusing electrode, which is just sort of directs the electrons into the opening in the accelerator. If I take that grid voltage and I make it positive with respect to the cathode, or I make it 0 with respect to the cathode, electrons can flow through the grid into the accelerator. And this can be done with a change of a couple of 100 volts, and I don't have to wait for the temperature to change. So a triode gun is more expensive, much more involved to manufacture, but it has this ability to turn the electron beam on and off extremely rapidly without changing the temperature of the cathode. So I can turn it on and off and turn it on and off and turn it on and off and have the fluence be the same each and every time. Here's a photo of a triode electron gun. Here's where it attaches to the accelerator. This green part is the insulator that insulates it from the anode. So all of this out here is anode. Everything behind it is reflector or cathode. We can see the reflector structure. You can see the grid structure. The silver disc behind it is the cathode surface. Here's a little better close-up of the cathode and the reflector. Here's our reflector. Here's the grid, is this screen, and the disc behind it is the emitting surface of this gun. Now, we talked about how we control energy when we were considering LINACS and accelerating structures. So now we're going to talk about dose rate control. In order to get a beam out of my accelerator, I need 2 things present in the accelerator at the same time. I need some electrons, and I need an accelerating potential in the form of that short burst of electromagnetic energy. If I change the pulse repetition frequency, I will change the dose rate, where what I'm calling dose rate is the monitor units per time on my machine. I would like to stay away from the word dose. I'm using it very loosely here. Although usually, we're talking centigrade per minute under some specific conditions. The pulse repetition frequency is the PRF. It is the number of pulses per second. How many times per second am I putting some electrons and the accelerating potential in the accelerator and letting them be accelerated? The other thing that controls dose rate is the dose per pulse, or fluence per pulse. At a fixed PRF, I can control dose per pulse by controlling the fluence of electrons leaving the injector. Or I can leave that the same and just change whether they're both present in the machine or not at the same time. So if I separate the accelerating potential and the gun pulse from each other in time and make them non-coincident, I will not get an accelerated beam pulse. This is how variant controls dose rate. They also have a PRF, although generally the machine runs at a fixed PRF. Historically, Siemens and Elekta both do PRF in order to control dose rate. And of course, if I'm at a different energy, the dose rate will be different if the particle fluence is different, because of course each particle carries a different amount of energy. So when I refer to dose per pulse or pulse repetition frequency or pulse dropping, I'm referring to it within the context of an energy. Here is question 3.
All right, it sounds like Christina's mic is still not working. So everyone go ahead and find the poll on the left-hand side of the screen and you can start answering the question. We'll give you about 45 more seconds to do so.
Again, we want the most correct answer, people. Well, based upon the response, I think they're ready.
I agree. Yeah, go ahead.
Okay. So which of the following is the most true regarding electron guns or injectors? Is it diode guns use low voltage pulses to control fluence? No, it is not. In a diode gun, the high voltage is used to control fluence, although really that's an on-off switch. Diode guns have 2 emitting elements, hence the name. No, a diode gun has 2 elements, but only one of them is emitting. Is it triode guns always have directly heated cathodes in medical LINACS? No, in fact, triode guns generally in medical LINACS seem to have dispensers, although that's not a hard and fast rule. Triode guns do utilize a third electrode, the grid, to rapidly control electron flow. Okay, moving forward. We've talked about accelerating structure, we've talked about particle injection, we've talked about RF devices. What remains is high voltage power supply and bending magnets. And I've got to go pretty quick here. So high voltage power supply, where do we get that high voltage for our RF system? This is the power source for the klystron or magnetron. What do we need? We need 50 to 100 kilovolts peak, very high current, short duration, and a particular pulse rate. The system has to charge in a few milliseconds because of the pulse rate, and then it has to discharge in a few microseconds. So we use a thing called a pulse-forming network. Functionally, the pulse-forming network is a capacitor. We charge it by placing voltage on it, filling it with current really, and then discharging it by connecting a conduction path. But a capacitor by itself charges and discharges with the same time constant, and we already said we want a long charge time and a short discharge time. So what we have to do is connect some capacitance and inductance in order to obtain these charge and discharge characteristics. So we have the pulse-forming network. It's a series of capacitors and inductors arranged in parallel, a serial parallel configuration. We charge C1 through C4 over a long period of time. And then when we close switch S1, C4 discharges through L4, then C3 discharges through L3 and L4, then C2 discharges. And the reason they do it sequentially is because until the voltage across this one drops, this one does not see any change in voltage because the inductors resist, inductors tend to resist current flow. So until this one has really begun to discharge, this one does not start. So in effect, we get a sequential discharge effect. The time is going to be 2 times the number of sections times the square root of L and C. And so if we choose our inductance and our capacitance carefully, we can get our 2.5 millisecond charge time and 6 microsecond discharge time. The PFN is part of the thing that is commonly called a modulator, and I'm going to cut this one off. The charge path is shown here. We're charging through the blue lines, okay? And the discharge path is these red lines. The discharge portion is the same on most medical LINACs. We charge the PFN up to some voltage, and then we discharge it by turning on a thyrotron, which is a high voltage switch. It's a gas-filled tube. The gas ionizes, it conducts. The charging method varies from manufacturer to a manufacturer, so in the name of time, I'm going to leave it alone. I do want to make sure that we talk about hydrogen thyrotrons. They're present in most of these machines. Functionally, it's a very high current, fast switch. It is an envelope filled with hydrogen or deuterium gas. It has a filament, a cathode, and an anode. It also can have up to 3 grids. When the anode is highly positive with respect to the cathode and the gas is at the right temperature and pressure, current will flow from cathode to anode until such time as the voltage difference is minimized, and then it just shuts itself off. We can prevent the current from flowing when there's a high voltage present on the anode with a grid structure. The grid is very close to the cathode, and so by making it negative with respect to the cathode, we render this positive potential invisible to the electrons that would like to leave the cathode. Once we make that 0 or positive with respect to the cathode, all of the gas ionizes extremely rapidly, current is conducted, and of course this is attached to our PFN, and the PFN discharges through this device and the high voltage transformer that then gives us the high voltage going to the klystron or the magnetron. The conduction is on the order of 3,000 to 5,000 amps per second. So it's extremely, they have an extremely fast on time. And of course, once this potential difference drops down, it just stops conducting. So, you know, that's that tube you see in the modulator with the blue glow coming out of it. Here's photos of a couple of types of thyrotrons. The one on the left is a glass envelope. The anode connection is at the top. The other connections are in the socket at the bottom. The anode proper is a circular plate in the top. And all of the other elements are actually located in the top third of the tube behind the screen. Here is a ceramic housed thyrotron. It's functionally the same. It's just designed to be immersed in a dielectric oil bath. Again, its anode connection is at the top. The grids and cathode connections and filament connections are made at the bottom. So that was our high voltage power supply section. On to bending magnets. Recall, we have the Lorentz-Force law that says that if we have an electron with some velocity in an electric field, that the force it will experience is going to be parallel to the electric field, but crosswise with the magnetic field. In other words, an electron with some velocity will constantly turn while it's in a magnetic field. So if I have an electron entering between the pole pieces of a magnet with some velocity, and if we turn that whole thing sideways so that the magnetic field's out of the page, that same electron will curve while it's in the magnetic field, and the radius of curvature depends upon mv over bq, which is basically the energy of the electron in the magnetic field. So the higher the electron energy, the larger the radius of curvature. In other words, it bends less. And lower energy electrons are bent more by a given magnetic field. We can take advantage of this in our LINAC if we have an electron beam that is entering a 90-degree sector dipole. So here the magnetic field is into the board, into the slide, excuse me. Electrons with higher energy are going to be bent through a larger radius. That's the red line. The E0, the central electrons, are going to go straight through at 90 degrees, and low energy electrons are going to be bent more. And our intrinsic electron beam leaving the accelerator is a spectrum of energies. In fact, it is a wider range of energies than we would like to use clinically. Now, if we can spread this beam out and clip off the unwanted sections, then we can get the beam energy we would like, and that is what we do. But we don't use a 90-degree bending magnet. This has a problem in that the energy distribution is also spatially distributed this way, and so that means that our patients would get high energy treatments near their head and low energy treatments near their feet. We don't want that. So what we do is, what one manufacturer has done historically is use 3 90-degree dipoles and place a pair of slits near the widest dispersion region, which chop off the highest and lowest unwanted energies. So if my energy limits are whatever E high is and whatever E low is, then the components of the electron beam that are higher than the red line and lower than the green line will simply hit these slit structures and make heat. And then what the other 2 sectors do is refocus the beam so that it can be extracted from the machine. Generally, this is a Varian LINAC 270-degree bending magnet structure. Usually we're talking a ±3% energy window on this system. If you happen to have a Varian TrueBeam, it utilizes a dual bend magnet. One portion of the bending magnet, the gap between the 2 pole pieces is narrower than the rest of the bending magnet, and so there's a much higher field region here at the top, and that's where the slits are placed. This allows the magnet to be shorter in height. Otherwise, it's very similar in function. We are spreading the beam out, we're blocking the highest and lowest parts of the beam, and then rotating the beam and refocusing it back for exit from the machine. If I happen to have an Electa machine, they're taking the same principles and applying them in a curve rather than in a circle. So the Electa accelerator is at an angle of approximately 22 degrees. It passes first through a 45-degree sector that bends the beam down, slits, a 45-degree sector that bends the beam back up, and then finally a 112.5-degree sector that bends the beam back down. We're doing the same thing. We're spreading the beam out, chopping off the unwanted portions, and then refocusing the beam. On the Electa system, this entire affair moves in and out to achieve high and low photons and electrons, to select different exit points, a target versus a window. And the advantage that Electa gets out of having it arranged this way is, number one, the accelerator is shorter. The top of the machine is not as tall as the Varian case. And they're actually bending it through fewer degrees, and so the beam emittance is reduced. And so the inherent beam spread is somewhat less than the other case. So now we have question number 4, Camille.
All right, I'm just about to make the poll live. Okay, you should see the poll again on the left-hand side of the screen. Please take the next 30 seconds or so to answer, and then Tim will go over the answers. All right, Tim.
Okay, got it. All right, in medical electron LINAC equipped with a bending magnet, what is the most important function of the bending magnet? Is it B, redirecting the beam from horizontal to vertical? That is one of the things it does, but it is not the most important function. Demagnetizing the electrons in the beam before they reach the patient? No. Adjustment of the intrinsic beam energy from the clinical beam? No, in fact, it's quite the opposite. We are selecting the clinical beam energy from the intrinsic energy spectrum. This is the main function of the bending magnet, is to get that narrow energy out of our machine for treatment. So now we can go to question 5.
All right, give me just about 15 seconds to load the new poll question. I'll announce as soon as it's ready.
Oh, okay, my apologies.
Oh, no problem. Okay, the poll is now live on the left-hand side. Go ahead and submit your answers. All right, Tim.
Yep. Okay. Yeah, looks like they're getting it. Okay, if we increase the amount of RF power being fed into an electron linear accelerator, what might happen to the electron beam entering the bending magnet system? What is the most correct answer? And this is probably the hardest question of the group. So, will the dose rate increase due to the higher PRF? No. We said nothing about PRF, so that's one of the silly ones. I see nobody answered that one. Intrinsic energy will increase. This is the correct answer, or the most correct answer. Now, dose per pulse will decrease. That one is also in the silly range. The hard one to sort out here is the clinical beam energy will load down. That could happen, but that's going to happen if we increase the amount of electron fluence, not the RF power. So intrinsic energy will increase. Yes, absolutely. All right, so that's it. You've had your tour of generic medical LINAC, at least for the particle injection accelerating structure bending magnet high voltage and RF system. We'll cover what comes after in the next lecture. I hope everybody found this interesting. Here are some excellent references. If you want to know more about linear accelerators, I strongly recommend Wangler and, of course, Karsmark. There are some free resources available, and I strongly encourage you to seek these out. Both of these are very, very good texts on accelerators. Thank you all very much. And I guess if we can, we could do questions.
Thanks, Tim. Yeah, if anybody has any questions asked Tim at this time, please enter those into the chat box. And we'll just pause for just a little bit until we get any questions in. I'll take a look on the YouTube channel as well.
All right. Any reason why you choose those boundary conditions? For what? Let me back off on that one for now. Let's see. Complexity equals profit. Thank you, Alex. A, Nikki. Really, the text. Okay, so that's a. Okay, so thank you. This was extremely helpful.
All right, last call for questions, anybody?
So I've got, it says there are 3 raised hands here. How do I deal with that?
Yeah, there's, if anybody has submitted that, please just ask your questions in the chat window. Oh, we've got one.
Okay.
From Scott, do you see it?
And I did the last slide there to show my email and stuff. Okay,
Perfect.
let me get back chat window. Okay, Scott, okay. Some of the Karsmark books are out of print. How do you get a copy? Yes, the slide says it's been out of print for a long time, and there are bootleg copies around. Unfortunately, that's the only way. Yeah, the one with the big red cover. Careful, Scott. Yeah. Anybody else?
All right, well, that looks like
All right.
all the questions for now. Thank you so much, Tim, for presenting this evening. We really appreciate it.
Thank you very much.
And thank you, everyone, for joining us for this free event that was hosted by all of us at WePassed. We'd like to invite you to join us for our next free webinar in the series on Thursday, January 26th at 12 p.m. Eastern Time with Justice Adamson, Assistant Professor of the Division of Radiation Physics and Department of Radiation Oncology at Duke University Medical Center on TG 142, Tips, Tricks, and Modern Techniques. For up-to-date information about any upcoming webinars, please follow WePassed on Facebook, Twitter. Be sure to take this short survey. You'll be redirected in just a minute. Good night.